All right, let's talk about linear regression. This is a very deep subject with lots of different ways of thinking about things. Let's start really basic. You can talk about linear regression without talking about probability and statistics at all, first of all. You can talk about it as purely like curve fitting, data fitting with curves. Let's start with a real simple example. Let's say we've got 3 data points. Oh, I'll draw them here, here, and here. Let's pretend we know the coordinates of these 3 points to be, say, 1, 2, 3, 2, and maybe I should make this one a little bit closer. 4, 3. 3 data points. Usually that's too small of a data set, but what am I after? I'm after a line of best fit. What's a line of best fit? There is no line that goes through these points exactly, right? They're not on the same line. What line goes through them best? Well, you could try to eyeball it. Maybe a line approximately like this. Well, I probably didn't make it with a big enough slope. Pretend I did. But what is that line? Again, you could try to eyeball it. You could say, well, the slope looks like it's maybe about, let's see, the slope between these 2 points would be rise over run 1/3, 1/3. I made this slope a little smaller, so maybe it's about 0.2 or so. And the y-intercept, maybe a little less than 2. So maybe it's y equals 0.2x plus 1.8 or something. You could try to eyeball it, but that's not very scientific. We probably shouldn't do such a thing. So we want to try to take a more scientific approach and say, well, you know, there's some slope m and there's some y-intercept b, and I just need to solve for them. Of course, m and b are used in calculus classes. In statistics, we use different letters. We use b1 for the slope and b0 for the intercept in statistics. b1's the slope, b0 is the intercept. So the question is, what are b1 and b0? That just begs the question, how do you decide? How do you decide in a scientific kind of way? And here's what people do. They minimize something. They minimize the sum of the squared residuals. What's a residual? A residual in this kind of context is a signed distance, a signed error. By signed, I mean S-I-G-N-E-D, as in plus or minus. This vertical distance, which is pretty small, gets squared. This vertical distance, which is pretty small and negative because the point is below the line, gets squared. And this vertical distance, which is a little larger, seemingly, gets squared as well. And then you add those up. You call that quantity SSE. SSE stands for sum of squared errors. Sum of squared errors. Errors is synonymous with residuals in statistics in this context. What are those things? What are these vertical distances? Well, remember, the equation of the line is unknown. We don't know its slope, we don't know its intercept, but we do know there's some slope and some intercept. What is this vertical distance going to be? Well, the second coordinate of this point, that's a data point, is 2. What's the second coordinate of this point on the graph of the line? Plug in 1 into this equation. this point right there that's supposed to be on the red line has coordinates 1, comma, plug in 1 here, B1 plus B0. So this vertical distance, if indeed 2 is bigger than that, is 2 minus B1 plus B0. I'm going to square it, so it really doesn't matter if for sure 2 is bigger than that or not. I could write it the other order because I'm squaring it. It's not going to affect things. That's a squared residual, a squared error in using this red line when x equals 1 to approximate the data point second coordinate of 2. We're trying to use the red line to approximate the data, to model them. For the next point, when x is 3, the y coordinate is 2 for the data point. What about the y coordinate on the red curve, the red line? Its first coordinate is 3. What's its second coordinate? Plug 3 into the unknown equation in place of x. 3b1 plus b0. Now, it looks like probably 3 is smaller than 3b1 plus b0. But again, once I subtract, I'm going to square, so it doesn't matter which one goes first. 3 minus 3b1 plus b0 is a negative quantity, most likely. As a residual, it's negative. As an error, it's negative. That's okay to keep track of the sign of the error. These are signed distances. This one would be negative. Question? Thank you. 2. Yep. That gets squared. And the last one, the second coordinate of the point is 3. For the red point on the red line, the coordinates are 4, comma, 4b1 plus b0. So now do 3 minus 4b1 plus b0. So there is, in an abstract sense, SSE for this unknown line of best fit. Should we also call it a linear regression line? Yes, we do. But it's probably best at the moment to call it a line of best fit, because just fitting the data. We're not thinking about statistics. You might even wonder what the word regression means. That's a little bit of a pun. So what do we want to do with this? What would make logical sense? Anybody got an idea? Minimize it. Yeah, I guess I mentioned that 5 minutes ago. Make it as small as possible. It's also not just called a line of best fit. It's not just called a linear regression line. It's also called a least squares line. Heard that phrase before? Least squares line? Maybe linear algebra. Talk about least squares in linear algebra. You can actually approach this with linear algebra. We're not doing that at the moment, but instead, we're going to approach it as a multivariable calculus problem. SSE is a function of the unknown quantities B0 and B1. I want to choose B0 and B1 to minimize this function of 2 variables. What does that mean doing? It means taking partial derivatives. Yay! You like partial derivatives? Maybe we should simplify these a little bit. Should I actually expand these squares out? You can, but you don't need to. And it's actually a little easier not to. But I will distribute the minus signs through the parentheses. You can expand these trinomials, but it's kind of a pain. It's not necessary. Take partial derivatives of this function SSE with respect to B0 and B1. If I differentiate with respect to B0, In each one of these terms, I need to bring down the 2. And then when I use the chain rule, I also need to multiply by the derivative of b0, which in each case is a -1. So I ultimately get -2 times in parentheses 2 minus b1 minus b0 minus 2 times in parentheses 2 minus 3b1 minus b0 minus 2 times in parentheses 3 minus 4b1 minus b0. Is it worth simplifying this? Yeah, probably, and not too hard. Distribute the -2 through, get -4 plus 2b1 plus 2b0 minus, next term, another -4 plus 6b1 plus 2b0 plus, or minus, excuse me, minus 6 plus 8b1 plus 2b0. I hope I don't make a mistake. Try to double check my work to hopefully catch any mistakes I make. Combine the constants, get -14. Combine the b1 terms, get 16 b1. Combine the b0 terms, it looks like we get plus 6b0. I need to set this equal to 0 to solve for b1 and b0. But not just that equation, I also need to take the partial derivative with respect to the other variable, b1. Which is a little trickier because with the chain rule, you don't always get a factor of -1. Here you get a factor of -1, here you get a factor of -3, here you get a factor of -4. We still always bring down the 2. So we get -2, 2b1 minus b0, minus, careful with the next one, -2 from the 2 coming down, times 3. The negative sign actually comes from the -3. 2 times -3 is -6. And with the last one, we get a 2 times -4 is -8. Simplify, -4 plus 2b1 plus 2b0 minus 12 plus 18b1 plus 6b0 minus 24 plus 32b1 plus 8b0. Double check things in your own mind, please, to catch any mistakes. I think we get a -40 plus the b1 terms give 52, it looks like 52 b1, 2 plus 18 plus 32. And the b0 terms give 2 plus 6 plus 8 is 16. We're going to set that equal to 0 and solve for b0 and b1. It's a system of 2 linear equations and 2 unknowns. Should we use row reduction in the calculator? Oh, what fun. Combining all your math stuff today. So much math. Stats. Oh, no. When I go to matrix mode, let's see. Math. No, I'm forgetting. Matrix. There we go. Edit. 2 rows, 3 columns. That is what I want. It's going to be an augmented matrix. I'm going to put the constants on the other side of the equation, the 14 and the 40. I guess I have b1 first and b0 second, though it could have been the other way around. 16, I'm looking at this one right now. 6, 14, 52, 16, 40. It's an augmented matrix like in linear algebra. These are the coefficients of b1 and b0 in each equation, and then the 14 and the 40 are on the other side of the equation. I want to row reduce this. Math, RREF. Guess not everybody's had linear algebra. Yeah, question? I moved those over to the other side of the equation in my mind. I know how you can convert these to fractions, but I forget how. Looks like B1 is approximately 0.2857. I think that should be 2 sevens probably. Right? Is that right? And B0 is approximately 1.571. 2 sevens. And what, 11 sevens? Yeah, probably exactly 2 sevens and 11 sevens are the answers. So it looks like our regression line, our line of best fit, our least squares line is y equals 2 sevenths x plus 11 sevenths. What did I guess unscientifically at first? I guessed 0.2x plus 1.8. It's really 0.2857x plus 1.571. A little bit bigger slope, a little smaller y-intercept. My drawing should be probably more like this. Is it really right? Can we use the calculator to find out? Stat menu. Edit. I'm going to start in list 3 and list 4 instead of list 1 and list 2 because I've got these in here for a different purpose. If you want to do list 1 and list 2, that's fine. Our data points are for x values were 1, 3, and 4. And our y values were 2, 2, and 3. Go back to the stat menu again. Calculate. Lin reg, that looks good. Linear regression. X is list 3. Y is list 4. Calculate. Slope is 0.2857. It's called A. Intercept is 1.571. It's called B. We will always call the slope B1 and the intercept B0. What's R squared and R? R is called the correlation coefficient. R squared is its square. It also has a name called the coefficient of determination. I'm not going to get into what those mean at the moment. Your calculator might not show R squared and R. If it doesn't, you can go to the catalog down to the D range of words. Oops. And go down to diagnostic on and click enter and it says done. And then you go back and do it again and R squared and R should be there. Diagnostic on. Why they don't make it the default, I don't know. Maybe on some calculators they do. What do you use this for? You use it to predict Y when you know X in statistics. Well, even in non-statistics. If you got some other X value, like 2, and you're trying to predict Y, use this equation. If X is 2, you get 2 sevenths times 2 is 4 sevenths plus 11 sevenths, 15 sevenths, slightly bigger than 2 would be the second coordinate of this point, which doesn't look like it is for the drawing. But again, my drawing was not as accurate as it could be. The line is really more like this. Is this really the best way to find the line of best fit? Not necessarily. You could debate. Instead of minimizing SSE, maybe we should minimize this expression. The absolute value of 2 minus B1 plus B0 plus the absolute value of 2 minus 3B1 plus B0 plus the absolute value of 3 minus 4B1 plus B0. Maybe we should minimize that instead. Why do we square? Well, if we were trying to minimize this, how do you do that with calculus? Absolute values, that's not differentiable. At most points, at least. Well, I mean, you could try. It is true that the absolute value of a number x is the square root of its square. It's x squared to the 1/2. And when you differentiate that, it is technically differentiable as long as x is not 0. You get x over the absolute value of x, actually, if x is not 0. But yeah, again, the absolute value function is not differentiable at 0, and that could be a problem. And if I related things to square roots, it would get even messier. This seems simpler. So that's one motivation for doing it this way, is it's simpler. I would notice that I would not want us to minimize the sum of the residuals themselves, because that could be, in fact, that's always 0. Well, okay. No. It could be positive or negative. You don't want to minimize the sums of the residuals themselves. You want to square them so you get positive quantities here. How is this done on Mathematica? And how is it done on a spreadsheet? On Mathematica, we could type the data in like this, say data, not DAFA, but data 1, 2, 3, 2, 4, 3 as a list of lists, a list of points. And the command to get a linear regression line from this in Mathematica is fit, capital F-I-T, data. Then you need to use that syntax. Yeah. The 1 and the x specifies you're trying to fit with a linear function. And this is just reinforcing the variable. If I would try to fit with a quadratic, I could do this. There's the best fitting quadratic. In fact, it should go through exactly through the points, because it's 3 points that are not all on a line. They would be on the same parabola. They're not all on the same vertical line either. But I'm after the line of best fit, and so I can do that. Spreadsheet. Plug in my points again. 1, 3, 4 for x. 2, 2, 3 for y. Probably the fastest way to see what the linear regression line is, unless there's some macro I'm missing that you could find, I've never searched for one, is to highlight the points, insert a chart that you want to be a scatter plot chart. Choose a scatter plot, which is just a bunch of points. Oh, come on, there it is, scatter. And on that scatter plot, you can choose to add the line in the equation and the line in the picture. I always forget, is it under series? Trend line, there it is. And you can also label it with the equation. There it is. Blank equals 0.286x plus 1.7. This blank is supposed to be the y, effectively. R squared is the squared correlation. It's about 0.571. I don't have to show that. That's the fastest way I personally know of to get it on a spreadsheet. What do we want to do for the rest of the day today, though, after having done all that? Let me first show you the formulas in the book for this stuff. B1, the slope, is this crazy fraction. You see summations of x's and y's. You also see summations of x times y's, summation of x squared values, and summation of x quantity squared. It's supposed to give you the slope. And then once you know the slope, the intercept can be found with this equation. Let's try this by hand for our example. It's not too bad. What do you have? calculator help as well too, but. So for our example, make a little table here by hand. Our points were what? 1, 3, 4 for X, 2, 2, 3 for Y. We're going to need to add the X's. This is going to be a sums row. Sum of the X's is 8. Add the Y's. Sum of the Y's is 7. In the formula, we also have to compute the X squared values and add those. So I square the X's and then I add them. I get 26. The formula also involved adding X times Y values. 1 times 2 is 2, 3 times 2 is 6, 4 times 3 is 12. Add those, get 20. Then the formula, let's see if I can remember it without looking. I'm not looking. See if I can remember it without looking. B1 was, can I do it? N times sum I goes from 1 to N, Xi, Yi. Am I right?
So far, so good.
So far, so good. Times, I believe it's the sum of the X's times the sum of the Y's. So far, so good.
Yes.
Divided by N times the sum of the Xi squareds minus the sum of the Xi's quantity squared, right? All right, I got it. N is 3 here, so we get 3 times 20 minus 8 times 7 all over 3 times 26 minus 8 squared. 60 minus 56 is 4. What was the answer? 4 sevenths? I forgot. 3 times 26 is what? 78 minus 64. 78 minus 64 is 14. Yeah. 2 sevenths. There we go. There's the 2 sevenths. B0 is a little easier to remember. Y bar minus B1 times X bar. The mean of the Y's is 7/3. Right? 7 divided by 3. N is 3. B1's 2 sevenths. X bar is 8/3. Get a common denominator of 21, I guess. 7 over 3 becomes 49 over 21. This is 14 over 21. So we get 35 over 21, which reduces to what? They're both divisible by 7. 5/3? No, that's not right.
16.
Oh, 16. Oh, thank you. 16. Done so much complex math today and I make that kind of mistake. 2 times 8 is 16. 33 over 21. Both of these are divisible by 3, it's 11 sevenths. Is that right? Is that what we got before? Yep. Okay. There we go. By the way, I didn't remember this formula just because I looked at it in the book 30 seconds before. I memorized the formula for B1 in a different way. And this is worthwhile to mention. We'll talk about it more next week. B1 can also be written as SS sub XY divided by SS sub XX, where I happen to remember, and you will find in section 11.2, that SS sub XY is this sum and SS sub XX is this sum. And then I happen to remember, you might wonder how, that numerator is the same as this. And I'm being a little sloppy with my summations now, just for the sake of time. And the denominator happens to be this. And then to get the formula in the book, I then just multiply the top and the bottom of this fraction by n. And that gives the formula in the book. I'm serious. This is how I remember it. Now you might wonder, like, well, how do I remember that this equals that? It's because I've taught it so much in statistical analysis in the business stats course. That's how I remember that this equals that. SS, once again, stands for sum of squares. Hey, that's a sum of squares. Wait a minute, that's not a sum of squares. Well, don't worry about it. It's just a label. Actually, the book doesn't always use the SS label, our book. But I like using SS for sum of squares. Again, after you multiply the top and the bottom of this by n, it simplifies to this one. I'm serious. That's how I remember it. Why does the intercept equal y bar minus b1 times x bar? That's some algebra that can be used to prove it. I will say that because of that fact, the point whose coordinates are the mean of the x's and the mean of the y's is always on the line of best fit. The mean of the x's, for our example, is 8/3. The mean of the y's is 7/3. 2.6 repeating and 2.3 repeating. The point 2.6 repeating, 2.3 repeating, it would be right around there. It's not a data point, but it's always on the regression line. And sometimes that's a useful fact to know, especially if you're trying to eyeball the regression line and if you happen to know X bar and Y bar. Hang with me a little more. You have 6 minutes left. Going back to the spreadsheet here. Let's get rid of this. I was hoping I would have time to do a little bit of ideas from section 11.2. I think I will not in 6 minutes. All this is being discussed without talking about inference yet. Nothing about confidence intervals, nothing about hypothesis testing. Guess what? That does come up next Tuesday. I was hoping to do some simulation with this example, quiz 1, quiz 2, to illustrate the ideas about how this is related to inference. But for the sake of time, let's end class by just computing the regression line with these fake quiz scores in a couple different ways. I mean, the quickest way would be, again, to graph this with a scatter plot and include the trend line. This is a new example, by the way. But here's what I like doing in a spreadsheet. Let's make a row labeled sums. Let's make a row labeled means. A row labeled SDs. A row labeled slope. A row labeled intercept. For the sums, I'm going to add the numbers up. So I'm going to do equals SUM, B2 through B11 in this case. I did choose n to be 10 here. So the means are just going to be the sums divided by 10. Fake quiz scores here. These are not real quiz scores. N is 10. I will go ahead and just divide this by 10 like that. I'm going to find the standard deviations, the sample standard deviations. Which, even though n is 10, are not necessarily nice numbers. And I'm going to show you one more formula for the slope. And actually, I'm going to add one number. Let me copy and paste these downward and add one number in here. I'm going to first compute something called the correlation, not correction. Correlation with the spreadsheet. This is what the calculator called R. And in a spreadsheet, it's equals correl with 2 R's and 1 L. It says data Y, comma data X, but you can actually do it in either order. I'm used to doing X first. I'll do B2 colon B11, comma C2 colon C11. 0.778 is the correlation. Being positive guarantees the slope is positive. If the correlation is negative, the slope is going to be negative. And in fact, there's one more formula for the slope that I want you to know that is not immediately in the reading. It equals the correlation times the standard deviation of the y values divided by the standard deviation of the x values. You could write that down. B1, another formula for it, is R times the ratio SY divided by SX. Just one S in each case because they're standard deviations. S sub Y divided by S sub X. And remember, this is a new example, so we're going to get a different slope than we got before. In this case, you can see it's about 1.02. And the intercept is the mean of the y's minus the slope we just found times the mean of the x's. Again, this is a different example. We get a different intercept, 0.14. Let's confirm, 2 minutes, that the formula in the book gives the same answers for the slope, again, with the spreadsheet. We're going to do more with the spreadsheet next Tuesday. So I'm going to compute a column for x squared. So that's x is the B2 column, or the B column. So here you can see I'm typing equals B2 squared. Is that big enough? Copy and paste that formula downward. And I also want the x times the y values, B2 times C2. 8 times 9, copy and paste that down. And in our last minute, let's confirm the slope again. First, by adding these columns, and then by using the formula in the book. B1, use the formula in the book. It's n, which is 10, times sum of the x times y's. That's in column E. That's this number here. Minus the sum of the x's times the sum of the y's. I'm going from memory here. Divided by n, 10, times the sum of the x squared values, minus the sum of the x's quantity squared. I know that was fast. It's the formula in the book, okay, with n equal to 10. That's what I'm using there. You can see 1.02, same answer. And that will end class today. Have a good weekend.